Welcome to one of the final high school submissions of my report. This is certainly what I'd consider to be going out with a bang. For those of you that haven't seen the breadboard versions of this, I'd recommend watching those videos for a more thorough understanding. In short, this is the PCB version of the CHUMP, a 4-bit programmable computer. It is 100% student-created and has had a few additions from the breadboard version. As a brief overview of the computer, it starts with the clock. As it pulsates, the program counter increments, telling the program ROM which line of code to execute. The lower nibble is a constant that can be used in instructions, whereas the upper nibble is the instruction itself. This is sent to the control ROM for interpretation. This IC's output is what tells the ALU what operation to perform, whether the RAM should be read from, and whether the accumulator should read in data. There are other control wires that have been made through logic, like the program counter load and the selector, but for now, we will consider that a part of the control ROM. Once the operation is put in place, the ALU performs it and stores the result in the accumulator for the next clock cycle. This result is then put back into one of the inputs of the ALU to allow for repeated operation of a number. The PCB is almost the same design as the breadboard, but of course there are a few modifications, the most apparent of which is the giant LED matrix that is controlled by 2 shift registers. The input pins of these shift registers are tied to the accumulator's output. Since giving the data to this matrix requires a minimum of 34 lines, the program counter must be extended. The second addition is the SN74LS93, a 4-bit counter with an option to reset. This chip will increment its output every time its clock input receives a falling edge. This means that pin will be tied to the most significant bit of the original program counter. Unfortunately, this chip does not have a load feature, but it can reset. Whenever the program jumps somewhere, the reset pin must be pulled high, clearing its output immediately. The difference with the program counter, however, is that it does it on the next clock cycle. This means that the reset of the SN74LS93 must be run through a flip-flop first, storing the signal for the next clock cycle. The final addition is this 20-pin header. It connects to my partner's board, the programmer. It has 2 switch banks, one for the address and one for the data. To flash a line into the ROM, the debounce button is pressed. This project was fantastic. I've loved every second of it. Thanks to Chris Darcy for facilitating 3 of the best years of my life, and thanks to James Corley, my partner in crime. Without him, none of this would have been possible, down to the original breadboard prototype. It's been a good year. Thanks, gentlemen.